Our next presentation is effective use of CFRP on deteriorated reinforced concrete members, case histories from Texas. Doug has 20 years with Texas DOT, primarily spent in an area office managing construction and maintenance projects.
All right, so today is going to be pretty much a show and tell, Texas history with CFRP wraps on deteriorated members. Be a lot of pictures, so I hope everybody enjoys photos. So we'll talk about impact damage to girders due to oversized load, referenced a little earlier, fire damage, some ASR damage, chloride-induced corrosion damage, up there in the regions that receive a lot of de-icing salts, as well as the marine environment corrosion damage, and a strange one, some early age cracking and a cast-in-place retaining wall. So just some random facts on Texas bridges. There's about 54,000 plus bridges on system, 35,000 that are on system and 13,000 or 18,000 off system. We do our routine inspections every year to make sure they're safe to the vehicles. And there is 27 international bridges between Texas and Mexico. As was kind of mentioned earlier, the bridges are getting pretty old. The age of these Texas bridges are about 42 years. But we do have a pretty good percent of most of these in fair good condition. Over last year, we had about 420 existing bridge contracts for replacement, widening, repair, rehabilitation, a little over $380 million. We also had 171 new bridges, over $297 million. So on to the first one again, CFRP wrap for impact damaged girders for oversized loads. That was the most widespread use of CFRP in Texas. We probably had approximately 100 repairs since 2000. As was mentioned, it's used to strengthen, restore the integrity, confine the patched beam repair, and add a sacrificial reinforcing for future impacts. That's kind of been noticed over time after we've made some of these repairs. We're using a longitudinal CFRP on the bottom flange of the beam combined with the U-wrap strips, which help enhance the performance and bonding. We've also started getting into the CFRP anchors with bidirectional plies added for increased shear and tensile strength. This was one of the earlier age bridges hit, I believe it was in 2003 out in Odessa. A lot of oil and gas, so we had plenty of oversized loads, probably no permitting. This beam was impacted, rupturing a lot of the web and flange. At the time would have probably been considered a full replacement, beam replacement, but it was determined we could go ahead and do the beam repairing in addition to the CFRP, so we did the longitudinal strip on the bottom flange combined with the U-wraps and opened it back up with saving many days, obviously not having to repair the whole beam and deck. I think it was 5 days and get it back open. Minimal cost compared to repairing the beam. Amarillo on an interstate, over the interstate, again another damage that would have been a complete beam replacement. It was repaired with concrete patching, epoxy injected the cracks, and then repaired with the CFRP wet layup. The saturator, as was mentioned earlier. So longitudinal, and you can see on the next slide the U-wrap strips on the bottom flange up through the girder web. Here they are, kind of the complete product. Then when you get to the final, we put the top coat on for the UV protection again, as was mentioned earlier. Here's a damage in Dallas in 07, another one over the interstate. This one was pretty much a complete punch through on the beam web and also the deck. Several pre-stressed strands were severed with the hole going all the way through the web. Bottom flange was ruptured, so therefore we went back in and retensioned. You can see on the right with the retention some of the splices, cable splices, and did the beam repair. I came in, did a crack injection on the remainder of the cracks. You can see on the right the longitudinal wrap on the bottom flange as well as the U-wraps, and then more additional U-wraps on the crack section of the girder. Top coat applied. This one was done in a couple of months, which again is saving a lot of time and a lot of money, disruption to traffic. Same structure was hit in 09. This was much worse, much more severe impact. It got to the second and third beam. I think the question was asked earlier, can this be done in-house? They basically had the state forces come out and do the beam repairs, splice in a few strands, and do the patching of the concrete, repaired the existing concrete beams with the new patching material, and added the, well, I missed that. There's where we had the 40 kip truck on top, which effectively preloads that beam and allows for that pre-compression or that preloading, and then once you remove that load after you've cured your concrete, you can get a compressive action on your patching material. This was a IH-20 in 2008, another pretty severe hit. Just did some small splicing, formed it up, patched our concrete. There's a pneumatic placement. Again, the pre-saturation is mentioned, and we got to have our surface prep proper. CSP 2 or 3 again was mentioned, which is an abrasive blast. Application of your epoxy resin for your undercoat and overcoat is critical for the bond and the polymer matrix fit up to work well. Again, you can see here the longitudinal bottom flange wrap as well as the U-wraps. U-wraps are usually placed at the termination points or your splice joints or on either side of our diaphragms. So again, at the either side of the diaphragms and termination points. This was a structure that took multiple hits in Dallas over Loop 12. It was beginning in 2006, a low clearance location, very significant impact. Well, it most definitely would have been a replacement beam. But we were able to splice several of the strands and place a CFRP wrap on it. It was hit again in 2008. You can tell here the CFRP fairly well mitigated the damage. It did, you can see, took out a couple of the spliced tendons, but probably made it a lot less severe as it would have been without the CFRP. So I think this is when we kind of started learning it acted as a sacrificial reinforcing. This was a third hit, this is the same second hit. So this was beams 2 and 3. We added additional cable splices, post-tensioned, and patched the material. Here's the end result with the beam patched and the CFRP installed. In 2009, we had the third hit. This was a fairly minor damage to the girder, which again kind of realized that these CFRP wraps can certainly add a sacrificial reinforcement on these multiple damage locations when the frequency of impact potential is fairly high. The CFRP isn't always needed to correct these beam impacts, but it certainly confines the patching material, and if you've got a potential for future impacts, it can give you a little bit of insurance on that next hit. Maybe you save a strand or two. Here was a recent one this last year. Oversized load came through and managed to get all 8 beams of 2 bridges. Pretty severe on all of them. Multiple strands were severed. The flange and web section were fractured. Anchorage zones were still intact, so it was determined we could go ahead and do the same repairs. So the concrete was removed and the surfaces were prepped. You can see the cable splices here. We did leave a couple, or at least one in this location, unspliced just due to the congestion of those grabbit splices. They tend to take up a lot of space, so sometimes you got to kind of lose a strand to get better concrete consolidation. But you see the steel was blasted clean, surfaces are nice and clean, and again formed up and shotcreted. Here in this picture you can see the 40 kip truck was used in the patching operation but then removed prior to your CFRP placement. This CFRP was used for confining and as strengthening. With the loss of those strands, that adds a little bit of strength and integrity. This one also utilized the Cfrp Anchors. These are kind of recently been utilized a little bit more often. They can increase the bond strength and the matrix can be substantially improved. Improving the ductility through redistribution of loads and can provide additional shear and moment strengthening. These anchors can be filled, created, or they can be provided by a supplier. Pretty simple little anchors to fab up and put in. This was a simple, or not simple, this was the detail of the repair. The bottom flange was wrapped entirely from the top of the flange all the way to the bottom, all the way to the other side, and then at each one of the anchor locations, several more plies, bi-directional plies were added with the anchor on top. So it was anchored through the plies and then brought out, again, just increasing the bond strength of that patch and ensuring a longer-term service life. These were the field installed anchors on that particular girder. So a few key points on repairing these impact damaged pre-stressed beams using the wet layup method. Surface prep is critical to all these externally bonded FRP systems. Surface must be clean and smooth. You want to grind the edges down so there's no pinch points at where the wrapping on the composite wrap. And as was mentioned earlier, we got the CSP 2 or 3 from the ICRI. Kind of what we're learning is we want to use plenty of epoxy resin for the under and overcoat. Serves as the bond and the polymer matrix. It's critical for the wet layup process and long-term performance. Closing portion of the bridge to minimize that superimposed live load stress in the beam will make the CFRP engage when the live load is essential for effective structural repair and strengthening. Again, we use the preload 40 kit truck, which pretensions the bottom flange where you're patching, and then once you remove it, kind of a pre-compression force happens and gives you a better, more of a locked-in patch, so to say, and then CFRP placed after you remove that load. Seems like we had very good performance. I guess once you put it up there and it doesn't get hit, you don't know if it's doing anything. I think recently we've had a couple of impacts, or at least one, where we noticed an entire section of wrap fall off the bottom of the beam, and we're associating it to surface prep, application of bonding resin. So I think inspection is critical and proper construction. Other than that particular location, I don't know that we've found anything different than that. But there is potential for UV damage, probably more likely on the glass fibers. The carbon fibers are pretty tolerant, but with the UV top coat, we haven't noticed anything to date. Moving on to some of the fire damage. This was a particular incident in '05 where a tanker truck went over the rail, slid under the bridge, caught on fire, burst into flames, burned for a couple hours. It ended up damaging 5 beams, 3 columns. The whole southeast interior bent cap was severely damaged. Damage cannot necessarily be assessed because of all the smoke and discoloration, so we had to get in there and do a lot of chipping, removing all the unsound concrete to expose the layers of discoloration and find where it was sound before we could determine any repair methods. It was kind of noted that the concrete cover effectively minimized the thermal. It was added a thermal protection from the fire, so we were losing a couple inches of concrete. Everything below that was in fairly decent condition. Discolored the concrete aggregate. You can see there it's a little pink, and obviously discolored the bearings and the reinforcing steel. That 2 inches of cover concrete is fairly critical in that compression zone and your bent caps and beams. So, and the tension zones. So we ended up wanting to go back with a full encapsulation of that cap, and again do the beam repairs with concrete repair and CFRP wrapping. That will go ahead and give us a little bit of additional structural capacity. So similar to our beam repairs, you chip out the unsound concrete and blast clean prior to your pneumatic concrete placement. Additional wire fabric was wrapped around the column to help engage that patch. On the right, you can see the reinforcing starting to go in for the bent cap encapsulation. It was cleaned off, sounded, cleaned, and then again just encapsulated in an additional bent cap with traditional concrete. Picture of the new reinforcing steel with the preliminary shotcrete system. Forms removed on that interior bent cap, a little oversized. The right picture where, again, you want to grind those edges smooth so you don't have any rough or corners where that CFRP ends up wrapping around your beams. Nice surface sandblast surface prep prior to your CFRP installation. In this situation, we just added one ply of longitudinal strips in the tension zone of the beam, and then the U-strips, again, wrapping up the beam web. Will enhance the structural integrity of the repair section, as well as reinforce the shotcrete cover concrete. 2 plies of horizontal CFRP were added on the columns, and effectively to adding confinement and strengthening. Again, we go back to the saturator, and the pre-impregnation of the fabric sheets was employed on this carbon fiber job. It's, again, critical to make sure you get plenty of bonding resins, make sure you get a good matrix, polymer matrix, as well as a good external bond to your structure. Getting close to the end with the cover top coat and the UV protection. Here's the completed project, which I think we could all imagine was a tremendous cost savings and a huge time reduction on the repair. It worked fairly well. Another use of CFRP wrapping. Some ASR damage was noted on another location, Lake Ivy in '04. This was only a 10-year-old bridge structure, started to exhibit the typical signs of ASR damage. It was going to be a pretty rough thing to try to repair or try to replace a new bridge that was only 10 years old. You notice the vertically oriented cracks were due to the restraint from the compression and the primary reinforcement. The light transverse reinforcement provided by the spirals was not sufficient to restrain the expanding concrete, resulting in these vertical cracks. So in this particular project, the surfaces were all sandblasted and clean. All the debris were removed out of the large cracks. 2 coats of an alcohol-based xylene were applied to exposed surfaces, and any cracks greater than .005 were sealed with a paintable acrylic latex. And then in an effort to waterproof the concrete, and then wrapped with the CFRP. This project did a checkerboard type wrap. It was probably pre-ACI 440 guidelines, I'm guessing, but somebody else could answer that, I'm sure. I think the intent was also to be able to monitor the future ASR swell potential. So the CFRP horizontal wraps were there to provide primary hoop confinement, and the vertical strips provided secondary reinforcing. Again, with the checkerboard pattern, we could continue to monitor the performance of the repair. Top coat was applied, and it continued to be monitored. Again, that was '04, so in '05 it was looked at, in '07 it was looked at, in '09 things appeared to be doing well, but a year or 2 later it was determined we weren't really getting what we wanted, so in 2012 we led another project to go back out and completely wrap these columns. We left the original checkerboard pattern in place because of difficulty in removal, and just did a full wrap around each column to do additional confinement. As of this time, recent inspection shows it seems that we've mitigated the swelling potential of the ASRs and extended the service life of this structure. So we're 15 years in on what would have been an early age problem on a 10-year bridge structure. This was an interesting project. It was probably back in 2000, one of the earlier projects we did. It was interesting to me because this technical report, 1774-2, had several iterations and research in it. It was very questionable on whether or not you wanted to wrap corrosion or chloride contaminated members. So the research was looked at, and it was set up that 16 structures would be selected to FRP wrapping and location in the regions where a lot of de-icing salts and brine and chemicals are used to get the snow and ice off the roads. So it had resulted in an aggressive chloride corrosion, and many of the members and the concrete members had been just completely eat up with horrible patching. So again, 1774-2 recommended to remove all the unsound concrete, get all the chloride contaminants out, abrasive blast the surfaces, as well as install some probes to monitor future corrosion activity. And then the concrete patching was to be done, and then the FRP was going to be installed. This particular project was one of the early ones, so it did use a lot of glass fiber on several of the structures. It was 3 layers of glass fiber wrap and then 1 layer of CFRP. Apparently at the time it was about the same cost just due to labor. Carbon fiber was extremely much more expensive, but 3 wraps of glass was similar to 1 wrap of carbon. So I want to keep in mind these are the before pictures of the extent of the damage. Again, this was widespread over many structures. Reinforcing steel was corroded. Delaminations was already coming off the columns all the way back down to the reinforcing steel. Extreme concrete deterioration. Bottom soffits of vent caps were torn up. But like we've mentioned, come in, remove all the in-down concrete, try to remove all your chloride contaminations. Picture on the left, you can see the steel has been blasted clean, kind of got rid of all that surface corrosion. Shotcreted and then hand finished to match the profile of the column. There's quite a bit of repairs. So I think the one on the right, if you can see it, several of these repairs had to be done half at a time just for the maintain the structural capacity of the structure with traffic. Prior to the wrapping, we installed a corrosion inhibitor, sprayed on a corrosion inhibitor to the columns and the vent caps. And then again, this is a wet layup saturator that was used for the resins on the glass fiber. These were UV resistant resins that were used on that glass fiber and thoroughly saturating to wet out the fiberglass and get a good bond and a good matrix. The primer's applied. So here's a section obviously of carbon fiber, confinement wraps on the columns. Continued on, and the little roller, as was mentioned again earlier, to kind of even out and get all the bubbles out of the material, try to get a good bond on your substrate. Getting close on the left to being completed with the bent line on all the columns having carbon fiber and starting the top coat there on the right. With the aesthetics looking much nicer. These were the completed structures. Again, back in 2000, due to the nature of the continued de-icing salts that were going to be used there, I don't think anybody was confident that these repairs would last. So that's why we chose the fiber wrapping. Multi-level interchanges would have been quite significant to replace. We had another follow-up in 2004. It was evident there was some staining, some minor cracking, but in general looked fairly good. I'll keep flipping through these pictures, and if you look at the superstructure where we didn't do any wrapping, you'll start seeing the continued acceleration of the damages that are occurring out there at this structure. So this is 2007 follow-up. Again, you might be able to see the beam ends are starting to show a little sign of age, a little cracking on the column, but in general, it's still in pretty good shape. 2007, again, similar, still have some of that staining. Starting to see the bottom soffit of the overhangs kind of showing signs of effervescence and a little fatigue, so to say. So follow-up research was 1774-4, which it came back out to the location and actually did some testing. Revealed the chloride penetration had been reduced. Assuming then the FRP had acted as a barrier, which would stop the ingress of chlorides and moisture into the system. Like I mentioned, some staining and cracking had occurred. They also went back and investigated the probes, and the values coming off the chloride levels showed that there was a high level of corrosion probability, but obviously since we covered it up, there was not really any evidence of corrosion, which would be the concern. So at this time, I kind of made an effort to get some additional information. I contacted some of our local research guys in the area, and they got out there and tried to, my question was, had we covered anything up? So they got out there and started doing some work in the last several months, or really the last month. This is a follow-up here in February of this year. Again, the magnitude of the structures were fairly significant, but they appeared to be visually in good shape, again with just some minor staining, minor impacts from vehicles or whatnot. Glass fiber looked to be intact. No significant UV damage was noticed. This is the particular bent line with the carbon fiber wrapping on it. Picture there on the right, you can see where another vehicle impact just kind of chipped a little bit of it off. But relatively speaking, no excessive problems with this particular structure. And this was, from what I was told by the engineer that was there on site at the time, that this was the worst particular structure, kind of like we saw at the beginning, where complete caps and columns were all wiped out. Here was a back wall that was repaired in that original project. Obviously, due to location, we couldn't wrap it. So, again, the concerns with the repairs not lasting for long was pretty much validated by this photo here. After 20 years, or a little less than 20 years, the repair's already fallen apart and really not doing any good anymore. We all talk about the bonding of that externally bonded CFRP. We always want to know we have a good bond. Managed to get some actual photos with the FLIR showing what you would assume to be some delaminations between the FRP and the substrate under the soffits of the bent caps, edge of the columns. May be a potential for trapping water, chlorides, or contaminants. Again, would give some concern. But as I mentioned earlier, we had some research go out there, do some field testing. I just got the information as of Friday and today, so I honestly haven't looked at it a whole lot, but it was very promising. Both the GFRP and the CFRP locations were tested. The results from the half cell measurements were negative or less negative than minus 2,000 millivolts, which per ASTM C876 concludes that there's less than a 90% probability that no corrosion is occurring at the reinforcing. It would be an amazing thing to assume that we've effectively stopped that ingress of chlorides and the continued problems that we were having out there. They did some cores, and their visual inspection actually kind of validated those conclusions. You can see there on the left, that's a exposed bar, and if we remember what it looked like prior to the original construction, that steel was in pretty bad way. So after the blast cleaning, we got a nice, decent looking rebar with very limited, or effectively no corrosion damage at this point. The efforts they made for their coring, I think you measured a little cracking there. Again, I haven't completely looked at what all they had, but I think he said that there's some cracking had occurred from the spiral. It was progressing to the outside layer of the column, but it appeared it stopped short of the interface, perhaps because of the confinement of the wrap. Could be possible, much volume restriction. They did some carbonation depth testing. Again, not having any information on where that particular test was. They measured about 3/4 of an inch of depth. So at this point in time, again, that would mean that we have still adequate cover on our reinforcing steel and have effectively mitigated some of this bad chloride issues that we had going on out there. So it seems very promising. This was down in the marine environments, probably due to an open joint, and poor consolidation on the bent cap at the time of construction. We ended up losing several stirrups due to the corrosion, a lot of deteriorated delaminated concrete. So it was utilized both vertical and 45-degree angle CFRP wrapping to increase the strengthening and repair the cap back to where it could be utilized. Also, galvanic anodes were added to protect for future corrosion. Cracks were injected. CFRP was installed per design in the 45-degree angles. Probably the final one here, this is the repair of the cast-in-place retaining wall, which was most likely maybe more of a geometry issue with the design. I think it was a drill shaft wall. Thickness of the wall changed, so there's a lot of early age cracking in the walls that could have potentially been a structural issue over time. The engineer wanted to go ahead and wrap it with 3 layers of glass fiber wrap, see what it would do. Here we are almost 18 years later. The wall's not showing any or exhibiting any reflective cracking through the GFRP. It also appears in aesthetic value, it still looks fairly nice. So I think left untouched for 18 years, that would have been a pretty pretty rough-looking retaining wall at this point in time. And again, it was several thousand feet of wall on both sides of the interstate, so getting 17 years of added value out of that it was obviously costly, but maybe a little UV coating will extend that even further.
Yeah, let's thank Doug. Thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.